Thanks to everyone for coming. So today we have a great pleasure to have Professor Yingbin Liang from Ohio State University. Professor Liang is a professor at electrical and computer engineering at OSU. She is also a core member of the Translational Data Analytics Institute and OSU. She is also the deputy director of the AI Edge Institute, funded by NSF at OSU as well. Professor Liang has done a lot of foundational research, including research in information theory, in optimization, in physical layer security, reinforcement learning, and other learning problems as well. She received the NSF Korea Award and also received the government's innovation reward from Hawaii, right? Before she joined OSU, she was also a faculty member at the University of Hawaii and the Syracuse University. So I personally have known Yingbin for almost 20 years now. She's an amazing scholar, ability to just work on any problem and make immediate impact. It's like very impressive. Like she pioneered the research on physical layer security. She started to work on machine learning before I know what deep neural network is. And every time I listen to her talk, I learn something new and interesting. I think today there will be no difference. So I look forward to a talk, and the floor is yours. Yeah.
Thank you so much for the nice work. Yeah, also thanks Lei and Qing for inviting me here to give a talk. Good afternoon, everyone. It's my great pleasure to talk about our recent work on the theoretical characterization for the forgetting and generalization performance for continual learning. And this is a joint work with Sen Lin, who used to be the postdoc at Ohio State, and Dr. Peizhong Ju, who is also a postdoc at Ohio State University, and Professor Nastro. So, no, it doesn't work. It used to work. Wait a minute. Sorry about that. Seems it got stuck. I guess I just use it manually. No, it doesn't even work manually.
The mouse.
Mm-hmm.
The mouse is just a screen out. Or now it's okay.
Let's see if it works. Okay,
Yeah.
good. All right. Sorry about that. First of all, let me talk about what is continual learning. So basically, continual learning deals with a set of tasks that actually arrives in a sequential manner, and then the agent need to deal with these tasks sequentially. So the goal is to mimic how human beings learn various skills during the lifelong time. And in the continual learning, one important issue is to address the forward knowledge transfer, because basically you would like to leverage the accumulated knowledge from the past tasks in order to design the new tasks so you get benefit. For example, in the human being case, suppose this person initially learned how to ride a motorcycle and drive a car and ride a boat. And then you can somehow imagine when this person needs to learn how to drive a truck, it will be easy for this person to do that, because this person can leverage the previous knowledge to be able to facilitate the learning of the new task. And on the other hand, the backward knowledge transfer is also important for continual learning, because you can somehow think of the learning of the new tasks will somehow backward strengthening this person's skill of dealing with some similar tasks. For example, if this person learned how to drive this truck, and then you somehow can imagine it's not so hard for this person to come back, and if he needs to drive a car, then it becomes much easier for this person to do that. So in the continual learning for the AI agent, it should also be the case that we should somehow use the later tasks to further strengthening the learning of the previous tasks. And there are quite many challenges when we design the continual learning. So one challenge is to deal with a privacy constraint, because once the task arrives, and then if you face the new task, then the previous data may not be available because it may belong to somebody else. So that you won't be able to come back and use the previous data to design a new tasks. And on the other hand, the AI agent may have the computational resource constraint and also the capacity power of the model that this AI agent is using. So for example, using a single DNN to deep neural networks to learn the later tasks may force this person to forget some of the previous skills. As an example, if we want to handle the classification task, suppose in the task 1, this agent need to classify between this cat and dog. And then, so suppose we train a neural network to be able to do that. And then later on, we have a new task arrives. Later on, we have a new task that arrives over here. So the AI agent needs to distinguish between the tiger and elephant. So we somehow can imagine using the previous neural network may not work over here. And then the AI agent may need to further train the neural network to be able to do this task for the new one. And then once the neural network is changed, then such a model, if I apply it again to the previous task, it may not work that well anymore because of the limited capacity of the neural network to deal with this task. But here is just a very simple example where I have only 2 tasks. In practice, you could see many tasks coming. And when you learn later tasks, it's possible if you use a limited capacity, use a model with limited capacity. It's hard, actually, it's very hard for the model to go back and still work well for the previous task. So this actually causes the major challenge for the continual learning design, which what we call as a catastrophic forgetting. So basically, if you use a neural network to design or model your prediction or other kind of tasks, so the neural network is observed to easily forget the knowledge of the old tasks when the neural network is trained to learn a new task. So mathematically, this figure actually illustrates what's going on. So suppose I have 2 tasks, task A and task B. And then suppose initially I train the neural network to fit the data in task A. Then it's not hard to expect the test loss or the performance of this model will drop very quickly for task A. However, if you use such a model to apply it to the task B, the performance may not change that much because it's not specially trained for task B. And then at some point, suppose task B arrives, and then we would like to learn task B now. So we further train the model to fit the data for task B. Then it also expected the performance for task B will drop. So you have a better performance for task B. However, now if you apply your model now to task A, then you can somehow expect that the performance will become worse and worse. So if I look at it at the level of the training parameter, this figure illustrates what's going on. So initially, when I train task A, I can start from some initial point of this model parameter. And then since I'm training it over the task A, using the task A's data, so the parameter will approach gradually to the minimal loss of this task A. And at this point, if I want to train it further to fit task B's data, then this model parameter may leave this global minimal for task A and move gradually to the global minimal of task B. So now you somehow don't expect if I apply such a model to task A again, then the test loss can be pretty large. So this basically illustrates when the neural network learns a new task, it's very easily for this model to fit pretty bad for the previous task. And this is called the catastrophic forgetting. So basically we call the neural network somehow forget the knowledge of task A when it learns a new task. So there have been very extensive research on designing various algorithms to deal with the catastrophic forgetting for the continual learning. And those work mainly focused on the experimental research. So they mainly focus on how to experimentally, how to improve the performance. There are actually quite limited theoretical understanding of the mechanism behind the continual learning. So one of the reasons is because, as you can somehow imagine, this model evolution over time when I have new tasks can get pretty complex, and it's actually pretty hard to analytically characterize what's going on there. And furthermore, since these tasks somehow, they're not fully independent, they could correlate it with each other, and that can further complicates the problem. So far there hasn't been analytical characterization of what's going on with exact form yet. So the current research, current theoretical research mainly fall into three categories. So the first category has several studies so far, but these studies mainly focus on a specific algorithm and understand what's the property of these algorithms. So essentially, they do not address the basic mechanism behind the continual learning. And there's a very interesting recent study on the training loss, how the training loss changes as we receive the new task for the continual learning, which is actually pretty interesting. And it's actually the work that motivated our study. But unfortunately, this study focused only on the training loss, not the testing loss, which is what we mainly care about in practice. So in general, we haven't seen any fundamental understanding on what factors are important for continual learning and how they actually affect the major performance of forgetting and testing error over here, or sometimes we call it the generalization performance. So this lack of theoretical understanding actually motivates our work to look at some basic performance characterization for continual learning. So as we can imagine, there could be several fundamental system parameters that can affect the performance of continual learning. For example, the number of samples in each task that can highly affect your performance, because that will indicate if you have sufficient training or if your training falls into underfitting or overfitting. And the number of model parameters is also important, not just in the sense of if it caused underfitting or overfitting. It also gave us the it also somehow determines the learning capacity. If your model really have the capacity to handle these many tasks that arrive sequentially. And of course, the noise level will also affect the performance. And in fact, in continual learning, another important factor that affects the performance is the similarity among the tasks. Because we can somehow imagine if you want to do the backward or forward knowledge transfer, there has to be correlation among these tasks so that you will be able to do that. And so our study will basically mainly focus on understanding how these model parameters will actually affect the performance. And the performance metric that we focus on, one is the generalization performance. So essentially, what is the testing performance when after you train your model? And the second issue is a main challenge in the continual learning, which is the forgetting issue, whether or not we can characterize analytically what's happening in the forgetting. And with that, how that will motivate us to develop new algorithms. So towards that, to that end, we focus on a linear model for in the continual learning tasks, and we would like to understand the previous issues that I mentioned. So more specifically, we assume there are T tasks arriving sequentially in time, and each task is a linear regression task. So basically, you have your data. You have your data generated randomly from a certain distribution. Here we assume the data generated from Gaussian distribution. And you have your ground truth model, which I denote by W star. And this T represents that's the T's task. And then the response is given by this inner product of the two corrupted by a Gaussian noise. And here we particularly are interested in the overparameterized regime in the sense that our ground truth can contain just contain a low dimensional vector, but the model that we use can be high dimensional. So the model so the number of model parameters we use, I did not write it here, but that's P that I'm going to introduce later on. And then we assume for each task, we have n data samples so that I can collect all these data samples together as a matrix. And then I can collect all these response values together as a vector and the noise into a vector. So I can compactly write up the response in terms of the input by this single equation. Again, so these data are generated IID by Gaussian distribution, and noise are IID, also Gaussian distribution. So how do we train the model? So here in our study, we focus on very basic algorithm that transfers knowledge from one task to the other. So what we did was the following. So initially, we start from zero initialization for the model parameter. And then when we receive the first task, we are going to train it starting from this initial point and train it until convergence. Okay, so then we get a W1 as a model parameter for task 1. And after we get a task 2, we are going to start from such a model parameter. So this one will serve as an initial parameter as a task transfer. And then we, again, will train the model parameter until the converge so that we get a W2 and so on. Eventually, we get so if we have T tasks, we eventually will train our model to WT. So we are going to, in our training, we use the mean square error to train the model. So it's given in this form, and so basically we can train the model either by GD or SGD approach. So in particular, we are interested in the overparameterized regime, and in which case we have this number of model parameter to be bigger than the number of samples that we receive. So if it's in the underparameterized regime, this loss function will just have a unique minimal value. But since it's an overparameterized regime, there can be multiple solutions that minimizes such a loss. And it can actually be shown that this is not in our work, but by other people already. It's a well-known result that if you train such a loss, starting from a certain initial point in the overparameterized regime, the algorithm will actually converge to the so-called minimal norm solution in the sense that it's going to be the global minimal, but it's going to be the global minimal that's closest to the initial point. So in our case, the initial point is the model trained from the previous task. So that's why it's closest to WT minus 1. So our, like what I said, our performance metric will be this forgetting and the generalization error. So first of all, suppose I have the tease task. So I have trained the tease task and get a model WJ. J's task and get a model WJ. And I could apply such a model to the previous task I, and then my performance is evaluated by the difference of this WJ with respect to WI. It can actually be shown that this is the same as the prediction error if I apply such a WJ to the I's task. And with such a notation, and the forgetting metric that we consider is as follows. So if we look at the picture over here, so in the end, we learn the model WT. But then we can apply such a WT to all these previous old tasks. And then if WT applied to the I's task, this is a performance. However, when I trained along the task I, this is a performance I get. Okay, so the difference between these two will be something we call as a forgetting. So that basically captures if I continue to train the model over the new tasks, how much performance difference I will have compared to the instantaneous loss function after I trained this task. So that's what we have over here as the forgetting of WT on the I's task. Yeah.
Could it be like WJ is also optimal solution for task I, just the weights are different?
Yeah, if that happens to be the case.
Then like the norm will not be 0, but actually the performance will be the same, right?
That's true. So if you have WJ, which is also the minimal value. That could be the case, I guess. Because you have many global minimums.
Right. In the, under parameter setting, then that cannot happen. But
in the if you have many global minimals and then you actually evaluate it.
Or maybe the global minimum are like far away from each other, so this cannot happen.
So actually, okay, so we write it in this way, but actually if you look at, so this can be shown to be equal to the prediction error. So if you talk about prediction error, that actually measures the actual loss function. And so this performance actually corresponds to the prediction error that you have for WJ.
Is because like maybe
because the data are ID.
Also maybe the global optimum are far away from each other, then you cannot actually get
you wouldn't, so what you mentioned wouldn't be the case mathematically.
Okay.
So intuitively, how to explain that, I need to think about it. Yeah. All right. Yeah, so that is the forgetting metric that we consider. And then we are also interested in the generalization error, in the sense that if I apply this final trained model WT to all these previous tasks, and what's going to be the average testing performance. So by definition, these two are correlated, but not exactly the same. So later on, we will see that, in fact, in some cases, they can be quite different. So before I introduce our result, let me first introduce two quantities that are important in our characterization. First one is the overparameterized ratio. So this R captures how the model is overparameterized. And the second one captures the task transfer code. We call it task transfer coefficient. So it's the form is given in this way. And later on, we will see how it plays a role in characterizing the forgetting and generalization. So our main result is actually given in this exact form or exact characterization of the forgetting and the generalization. So if you look at the form, each of them contains three terms. So the last term captures how the noise will affect the forgetting and generalization. And the middle term, you can see it's a difference between the two task models. So it actually captures how the dissimilarity of these tasks will affect the forgetting and the generalization. And the first term captures how well we learn the ground truth model of these tasks. And this, to our best knowledge, is the first explicit form of this forgetting and generalization error. And in fact, throughout the rest of the talk, I'm going to explain what has been captured by these two expressions. So I will focus on the how the three main parameters affect these performances. The first one is overparameterization. As I said, it's captured in this R, the ratio. As you can see, it shows up in all of these terms, okay? And the second one is a task similarity that mainly affect these two terms over here. So if we have this distance to be smaller, that means the tasks are similar. But of course, it's arguably the task similarity metric because there could be all kinds of metric for the task similarity, depends on the application. But this is the one that we consider here. And we are also interested in to see how the task ordering will affect this performance. Meaning that if I have the control of how to order the tasks when they come sequentially, then that will also significantly affect this forgetting and generalization. And the task ordering are actually captured by this task transfer coefficient associated with this task similarity over here. So next, let me talk about each of these parameters and how they affect this performance. So let's first focus on the overparameterization and first on the forgetting. So this is a form that we have seen in the previous slide. So first of all, so as we can see, if I have an overparameterized model, especially when I take this P goes to infinity, that means the model is extremely overparameterized. Then what's going to happen? Clearly, this term will decrease. Okay, if you can see the form, the R is N over P, P goes to infinity, R goes to 1, so Cij becomes 0. And it's not hard to understand why this form, why this term will decrease, because if you have more model capacity, it will help to accommodate new tasks so that you will have less forgetting. And actually, the first term and the third term will also go to 0, essentially tell us if we have more parameters, extremely more parameters, eventually we will actually have 0 forgetting. But in fact, it turns out how this forgetting goes to 0, it may not be some monotone process. So to illustrate that, let me look into a specific example. Suppose I have 2 tasks over here. And again, we are looking at the overparameterized regime. So the forgetting can be simplified into the following form. Okay, so first of all, maybe it's instructive to first look at these 2 figures. So we have the figure 1 to have all these tasks to be exactly the same. So this basically tells us the extreme case when the tasks are extremely similar. And the second one is when I have orthogonal ground truths. So you can think of them as the tasks are extremely different, so dissimilar. And no matter if I'm in this case or in such a case, as you can see, so this is where the overparameterized regime starts. And then the forgetting starts to drop, and eventually it will increase into the 0 forgetting. And for the second one, again, starting from the overparameterized regime, again, the forgetting will drop eventually to the 0 forgetting. But now you may already observe that in the second task, it's monotonically decrease. But for the first one, it actually first decrease and increase. So that can actually be explained by this expression over here. So if we look closely how each of these terms changes with this P, that is over a number of parameters, clearly these 2 terms, as P increases, they will decrease to 0. Okay. However, the first one, if you look at the first one, so P effect is R, but the first one, the first coefficient will actually first decrease and then increase as P increases. So that is actually what we see in such a case. But why you didn't see it over here? Because you only see such a decrease and increase only when this term becomes dominant. Okay, so this term becomes dominant only when you have a very small similarity, very small dissimilarity, so the tasks are similar, and when you have a small noise, so that you can observe this decrease and increase. Okay, and then so clearly, so in this A case, we have a extremely similar task, so that this term actually becomes 0. And you actually do not see it in all the curve, but only these 2 because they have lower noise. Okay, that exactly verifies what we have seen over here. And another phenomena I would like to emphasize over here is that from here you can actually see that I start from the 0 forgetting, and then I drop to the negative forgetting. So then what's happening here, that actually infers the backward knowledge transfer in the sense that when I continue to learn the same task, that will actually strengthening my learning happened in the old tasks because they are all the same. So you kind of get these strengthened task learning in the backward transfer manner. So that's why you can see the negative forgetting over here. Okay, so next, let's move on to talk about how the overparameterization will affect the generalization performance. Okay, so over here, as we can see that the second term and the third term for the generalization, they eventually will approach 0 as P go to infinity. So essentially, it's not hard to explain over here what's happening because you have more model capacity so that your final trained model will be easier to fit into those old tasks so that your test error can be very small. And this descent behavior also gave us the performance in the overparameterized regime. As we can see in both cases, we do have the generalization error decrease. And furthermore, you also have seen that it's not monotonic like what we have seen in the forgetting case, but here it's a little bit different in the generalization error. So before I talk about that, let me first talk about what we call as a benign overfitting. So benign overfitting basically means when we have, so this has been a phenomenon already observed, not in the continual learning, but in the single task learning already. But in the continual learning, it has some different, has certain different impact due to some different reasons. Okay. So basically, I look at the overparameterized regime starting from here and starting from here. And as you can see in the overparameterized regime, I do have the testing error can drop. And in particular, in some cases, I could have the smallest testing error to be even smaller than the smallest testing error in the underparameterized regime. So why could that happen? Because in the underparameterized regime, your test error will essentially be controlled by the task similarity, dissimilarity, and the noise level. However, in the overparameterized regime, due to the model capacity can increase, so both of this term can drop. So eventually, together with the first term, you can somehow imagine as if these two terms dominate the performance, you would see the minimal test error will become lower than the minimal test error in the underparameterized regime. So this is what we call as a benign overfitting. So next, let me move on to explain in what cases we will see such a descent floor or non-monotonic behavior of the testing error. So again, let's look at the case when we have two tasks, and we can express the generalization in this specific, actually simpler form. If we want to see how this generalization error changes as this P increases, what we can do is to take a derivative of this generalization error over this P. And this is what we have. And now you can take a further look at what's going on here. So essentially, this second term associated with sigma square is actually a negative, meaning that if this term dominates, I'm going to have a generalization error to drop. Okay, and then the first term is actually captured by the inner product between these two tasks. So that can be interpreted as a correlation between the two tasks. So if this correlation is very small, essentially only this one dominates the performance. Okay, so that basically when we have tasks to be extremely dissimilar, and then the second term will dominate the performance. So that's why I will just see the descent curve. So that's reflected in this second case when we have tasks to be extremely dissimilar. However, if I have tasks to be very similar, so my first term can at some time, at some point, take over this entire expression so that I can have a positive derivative. So in that case, I can have the generalization error to first drop, dominated by this one, and then increase. Okay, first drop and then increase, because at some point this term will actually take over. Okay. So next, let me focus on the task similarity and talk about how that will affect the generalization performance. So this is a term that how the task dissimilarity will affect the generalization performance. And in particular, we can note that this coefficient over here is always positive. So that actually implies a very simple fact. So the generalization error will monotonically decrease. So it's going to decrease as the task becomes similar. However, this may not be the case for the forgetting. So at a high level, if we think about the forgetting, we would imagine as a task becomes similar, it becomes harder to forget the old task. So you will basically have, so we expect more similarity will imply less forgetting. Turns out this may not always be the case. So if we look at the term that affect this forgetting by this dissimilarity, so here the dissimilarity is affected not just by the value of this term, but also this coefficient over here. And in particular, such a coefficient can actually be negative at some point. Okay? Especially if you look at this form, it can actually be negative if this term becomes very large and the other two terms become small. So since it's not always positive, so that potentially implies the fact I could have more dissimilarity but less forgetting. So let's look at some special case. So if I have two tasks, then you can actually easily see that the C12 turns out to be bigger than 0. So that tells us there is a less, so if tasks are more similar and there's less forgetting. So this somehow agrees with what we somehow intuitively expect. And this actually can also be verified by our experiment. So basically, the horizontal axis so we have two tasks, and horizontal axis represent how many overlapping classes that these two tasks have. So basically, as a number becomes bigger, we have tasks to be more similar. And as a task become more similar, we have both the generalization to decrease and the forgetting to decrease. So this basically is not so surprising result. However, if we go to the second case, so suppose we have 4 tasks, okay, and then you can actually see that this coefficient may not always be positive. In particular, we can actually design the task so that the C12, we can design the first 2 tasks so that the C12 is less than 0. If it's less than 0, that will imply when we have tasks to be more similar, then we have more forgetting overall. So intuitively, how we explain that, it actually took us some time to understand it. So intuitively, how you can think of the case is as follows. So if I initially have 2 tasks, which are very similar, so basically for the second task, it will extremely strengthening my learn of the first task. So that will shift the model parameter towards certain subspace, okay? Extremely towards a certain subspace. And then when you learn new tasks, that can be far away from the strengthened model parameter so that you actually have more forgetting, even when you have a more similar task. So this could be some explanation we can think of to explain what's happening here. But that mathematically, this is what happens. And in the experiment, we can demonstrate over the 4 tasks. So basically, the 3 curves over here represents the 3 scenarios we can have. Then these numbers represents the number of overlapping classes. Again, when you have a bigger number, you have more overlapping classes, so you have the tasks to be more similar. Clearly, as we can see, as the tasks become more similar, if we look at the blue curve, clearly you have a more forgetting.
What do you mean by overlapping classes?
Also, essentially, when we design the experiment, the first experiment can be the classification problem. And the second experiment can also be another, so the second task can be another classification problem. And then the first problem can be distinguished between cat, dog, and bird, for example. And the second one can be distinguished between cat, dog, and something else, okay, elephant. So then you have two overlapping classes in this case. The bird and dog are the overlapping classes. Alternatively, I could just have bird to be overlapping classes for the first two tasks.
Okay, then in that sense, I think like X, the distribution of X changes over the tasks.
The distribution of X.
Yeah, I think, but when you like previously, when taking the expectation, I think it's expected over X.
Yes.
And is it like previous formula, does it applies to like the assumption that X over every tasks?
Yeah, it's a good question. So these are actually the experiment we did over the neural networks. Certainly the data may not satisfy our previous assumption when we characterize the theoretical result. So the point here is to say that the insight that we captured in the theoretical form will actually carry over to the practical experiments, even when the assumptions are not fully satisfied.
But the theory was based on the linear models, right?
Yes.
And
yes.
this is the experiment
Yes.
on like the classification.
It's a neural network model. It's not a linear model anymore.
I see.
So that's the point that we are saying that so the actual phenomena may not be limited to the theoretical assumptions.
So here you are like doing the pairwise distance of the task similarity. So when we doing this ordering, should we like when we're adding a new task, should we compare to the similarity to our previous?
So actually in this experiment, we did a pretty special case. So we have the tasks 3 and 4, their ground truths are orthogonal to the first two. And then the first two, I can change their overlapping classes without affect the later tasks, so that I can control the similarity between the first two. But they are orthogonal to the last two, so that doesn't affect. So basically, I can control it. If I make the first two more similar, the overall all of the tasks are more similar.
Just a follow up this. So when you are change the task from some class classification to other class, they may have overlap. Does the training data also change?
Yeah, that's training data. So if I have the bird to be the
Yeah.
overlapping, so the training data will contain the bird images.
Yeah, but I mean, in this case, how do you like decompose or distinguish the generalization between the data set or generalization between the task?
Also, the generalization, I basically learn a model, and so to just apply it to the previous task.
I say, for example, if the task is kept the same, we're still doing the classification on the same categories, but we kind of like change the data set, right, to contain some like new data or something. Do you think?
Yeah, I guess you have a good point. I see your point. So you're saying, suppose previously I distinguished between bird and dog, and now I distinguish between bird and cat. And then I learned the model between bird and cat. So I will just apply this model to the previous task.
I see.
And distinguish between bird and the dog.
I see.
But it could be the case when you apply it back, you actually need to kind of switch your category index,
Yeah.
so that it will find the right class that it actually distinguishes.
I
Yes,
see. I see.
yeah.
Yeah. Thank you.
Yeah, so finally, let me get to how the task ordering will affect the forgetting and generalization. So this is under the assumption, suppose I can actually control which task will arrive at which time. So from the expression, again, the task ordering will affect the term over here, the second term in the forgetting. And suppose we have, let's say, suppose we have big dissimilarity. And then how you can ask the question how I should order these two tasks so that can minimize my forgetting. And if I look at the this coefficient over here, we would think that when these tasks are very dissimilar, I would like to try to make this Cij to be as small as possible so that I can minimize my forgetting. So how do I do that? How this Cij will be affected by the ordering. First of all, if I look at this term, I want to make it as negative as possible. So that will require me to make both to make I and j to be adjacent. And then I want to make these two to be small. Okay, then that will require me to make both I and j to be smaller or in the early stage. Turns out this is actually a quite complicated expression. To give us any, so far we haven't really seen one general principle that applicable to all the scenarios yet. What we have seen are these special cases that we start with. So the first case is what we call as one versus many. Basically, suppose we have t tasks, they belong to two categories, and this red one indicates there's one task that's different from all the remaining ones, because all the remaining ones belong to one category, and then we have one special task. So the question is, how should I place this special task so that I get a minimized forget? Anybody would like to make a guess? What would be the minimal ordering that minimizes the forgetting? Intuitively, should we play this task earlier or later? Later? Earlier. So if you think about it, if you play it later, what will happen? So that will highly affect your model, final model that you learn. But don't forget, your majority of the tasks are different from this one. So that will cause a lot of forgetting. So this will actually suggest that we should place this task to be earlier, so that later on my learning will be strengthened by the same category of tasks, so that I don't have that much forgetting, at least for majority of the tasks. So we have the theorem to tell us that in this overparameterized regime, this so that we use I star to represent the optimal location. Turns out it can take any integer value between it has to be placed in the first half of the sequence. But where is the optimal location will depend on your overparameterized model P. So if this P increases, that will push this task to be earlier. Okay. So that's actually what we get from this proposition. And if you look at what happens, so if you look at the figure over here, so we use this number to represent the location of the special task. So from here, you can see that in all three scenarios, we always see the minimal forgetting happens in the first half locations, but depending on your P. And secondly, we study another case. Actually, I should make it to show up in this one first. So we have this. Wait a minute. Actually, I think this is a wrong figure here. Sorry about that. Okay, so look at the theorem, but forget this figure here. So here we consider the equal occurrence case. Okay, meaning that suppose we have two categories again, but each category will have the same number of tasks. Okay, so in this case, our theorem tells us we should alternatingly place these tasks so that we can strengthening the learning of each category continuously over time. All right, so in this experiment, it also verifies what we characterize in the theorem. So here, 0 and 1 represent the alternating placing these tasks, depending on which task you place first or which task you place second. And then the other numbers represent the other ordering of these tasks. So clearly from here, you can see that the minimal forgetting always achieves either at 0 or 1. That means we alternatingly placing these tasks. Okay. So next, we want to look at how the ordering will affect the generalization. So, turns out it's not always the same with how we should place these tasks for minimizing the forgetting. In particular, for the case 1, when we have 1 versus many, but if we want to minimize the generalization error, we should actually place the special task in the first place, always. That always minimizes the generalization error. But for the second task, we do have these. So for the second task, we do have the alternating placing these tasks will actually give us the minimal generalization error. So this example basically tells us the ordering that minimizes the forgetting and minimizes the generalization are not always the same. So next, let me quickly talk about what can this theory further do for us. So, in this case, we can consider a simple problem. We would like to design a scheme for the forward knowledge transfer. And we are asking the following question. So if we use, because in our scheme, we take the previous task knowledge simply by the initialization. And we ask the question, if I use the previous task as the initialization, what's the difference between this model with the optimal, with the ground truth model, versus if I take any random initialization, simply do not do any knowledge transfer. So this is so this forward knowledge transfer is captured in such a form, and in particular, if you look at this similarity between the tasks, and we have this coefficient to indicate if I have these 2 tasks. Okay, so their role the role that the tasks plays on this task T is different depending on if I is close to T or if it's far away. So it basically suggests that the closest task to this T will actually play a more or will somehow dominates the performance. So this motivates us to develop a further algorithm compared to the previous one, where we place more weight for the for the closer old tasks, so that it can play a more role to minimize the forgetting, actually to minimize the generalization. As you can see, such a designed model indeed turns out to be better than the previous vanilla model in both the testing performance and the forgetting. So this sort of closes my presentation. So as a summary, we provide a explicit form for this expected forgetting and generalization error. Turns out such a form helps us to draw a lot of insights about what's happening and how these task similarity, task ordering, and overparameterization will affect this performance. there could be a lot of space to generalize such a study or extend such a study. For example, we addressed only the linear model, but certainly it will be very interesting to extend the analysis to be able to address neural networks. And there could be also a lot of other directions that we can take from here. For example, study the decentralized or federated learning algorithms, or here we focus on the classification tasks. There could be a lot of space to work on other potential tasks, like, for example, the reinforcement learning tasks and so on. So for those people who are interested in learning more details about this work, this is a published paper in this year's ICML, and you can also find the work in the archive. And thank you very much, and questions.
The theory here, like, so this is for linear models. So, is this working? This method that you designed here working on nonlinear networks empirically?
Yeah. So some of the experiments I showed, indeed, they verifies our theory, even in the neural network setting. We consider small neural network, but at least it's a demonstration that these results can actually carry over to the nonlinear models.
So for nonlinear network, are you like for each stage you are fine tuning the whole fully fine tune your model, or I think you can do partial fine tuning. So I think there could be also.
Sure. Yes. Yeah. That's actually a very interesting point. Definitely, you can study how partial you train the network will affect your performance. I guess that will also depend on how similar the tasks are. And,
yes.
Yeah.
Yeah, your analysis applies to regression setting, or why experiments on classification?
Oh, that's a good question. We actually never thought about this here. So I guess what we want to demonstrate is that your result for regression will also carry over to classification tasks. Certainly, we do have the simulations on the regression task that actually exactly match what we have over here. I didn't show them here. Yeah.
Throughout your talk, in most of your figures, you mostly had the number of parameters P varied on the x-axis. And in a couple of slides, you stated theorems or corollaries for when the number of tasks was small, like 2 or 4 or 6. I'm curious if you ever looked at how these plots and formulas varied when you only varied the number of tasks. So if you look at 1 or 2 tasks, you see how does the generalization and forgetting error. Then when you add another task, then another task, and then another task, and you keep looking at all of those in a whole long sequence.
Yeah, that's a good question. We haven't done that yet, but you can somehow imagine if you have new tasks, then there will be a lot of complication in the sense that if you add similar tasks or dissimilar tasks, that will significantly change the setup and the expression. Yeah, that's actually one challenge to try to extract some. We actually tried to extract some more universal insights from these expressions, but turns out it could be very difficult, simply because you could have many dimensions of the change that you can make when you have new tasks.
Another follow-up question I have is, when you were talking about how when you have like many similar tasks and only one dissimilar one, and you said it was best or optimal to place that dissimilar task towards the beginning of the training. I can see how that it would minimize the generalization error just because you're looking at everything in aggregate as an average. But did you actually look at the specific errors of each of those terms to see how well, if you let's say you do the dissimilar task at T1, and then you have 9 other tasks that are similar. And in average, I can see how that would make your generalization or forgetting error small. But did you ever look at how that training affected just that dissimilar task? Because that could be the large error when the other ones are small.
That's true. We didn't really look at the individual error, but you can somehow imagine if you learn the tasks, the same tasks later, and your biggest testing error will come from that special task, right? Because when you learn the same task, it will play the same for all these same tasks. But for that special one, because it's specially so it's specially trained to fit those task data, then its test error for the special one will become very large. That's something I can imagine, but I actually didn't look at the individual test error that come out of the experiment, but that's what I can somehow expect.
Any question from the Zoom audience? If you have, feel free to unmute yourself and ask. If not, let's thank the speaker again.